In chapters 1 and 2, we discussed extensively the first and second laws of thermodynamics, investigating first the transformations of energy from one form into another, and studying second the criteria for spontaneity and for reversibility. In the next 3 chapters, we examined various applications of these laws to phenomena of importance in the chemical and life sciences. Chapter 3 is composed of 2 distinct parts. In the first part, we deal with phase equilibrium and phase change in single component systems, while in the second part, we discuss mixing or multiple component phase equilibria. In preceding science classes, you have been exposed to the concept of phase transition, such as crystallization, vaporization, and so on. You have heard about phase diagrams, and you've been told that phase diagrams provide a map explaining which among the solid, liquid, and gas phases is stable under specific conditions of temperature and pressure. In this chapter, we will put these phase diagrams on more serious footing by deriving equations of pressure as a function of temperature that show where these phases are in equilibrium. We will also show that the concept of phase stability and phase transitions can be extended to systems of great importance in the life sciences, and discuss protein folding and DNA unzipping. In this first lecture, we focus on the thermodynamic implications of phase stability. The study of how processes develop with time belongs to the line of scientific inquiry called kinetics, a field very different from thermodynamics. Considering phase transitions from the standpoint of their time evolution is, however, very useful. Assume, for instance, that you remove ice cubes from a freezer at 15 degrees Fahrenheit and place them in an empty glass at room temperature and ambient pressure. You will observe that the ice cubes will slowly warm up to a temperature of 32 degrees Fahrenheit, that is 0 degrees Celsius, where they will start melting. They will remain at that temperature until they have completely melted, after which their temperature will rise again to the temperature of the room the experiment is carried out. From such an experiment, we conclude that under ambient temperature and pressure, say 70 degrees and 1 atmosphere, water liquid is more stable than ice. We conclude also that during the solid to liquid phase change, the temperature remains at 32 degrees Fahrenheit, or 0 degrees Celsius, and the pressure remains constant. We also conclude that at 70 degrees Fahrenheit and 1 atmosphere, the transformation H2O solid to H2O liquid is spontaneous. Hence, its associated delta G is negative. Over the next few slides, we will discuss more thoroughly what we mean by phase stability, considering what happens to a pure substance as you increase or decrease either its temperature or its pressure.